Precipitation reactions. Once again, this is an addendum to double displacement reactions. Now, precipitation reactions are those where you may end up forming a solid upon combining two liquid substances, specifically two solutions. And in order to figure out whether you will end up with a solid upon mixing two substances together or not, we have to talk about something known as solubility rules. The solubility rules are general, they're not the most comprehensive, but they cover the most common ions that you get to interact with in a chemistry lab, at least at this stage. And specifically, solubility rules say that if you have ammonium or any of the alkali metals, so lithium, sodium, potassium, rubidium, or cesium, associated with an ionic salt, the ionic salt is expected to be soluble, or AQ, as far as the state of the ionic salt goes. And by the same logic, if your ionic salt contains nitrate, acetate, perchlorate, or even chlorate, the salt is expected to be soluble, irrespective of the identity of the cation. These are the always soluble cations and anions, and I would recommend that you do memorize this particular list, at the very least, to expedite the process of determining whether something will remain soluble or insoluble in solution. Okay, now, when you start getting to the halogens, the story gets a little bit more complicated. Specifically, chloride, bromide, and iodide. Usually, these particular anions are soluble with any cation, but there are some exceptions. If we do mix chloride, bromide, or iodide with either silver plus, mercury 1, or lead 2 plus, you expect instead to get a solid product, an insoluble solid, in other words. Any other cation that's not listed here, you expect to be soluble with chloride, bromide, and iodide. Sulfate is kind of similar. You expect sulfur compounds to be soluble unless you mix them with calcium 2 plus, strontium 2 plus, barium 2 plus, lead 2 plus. Usually big cations with a 2 plus charge. That's where sulfate tends to be insoluble with. We will investigate the reasons for why this is later in the class. Now, on the other hand, hydroxide and sulfide, they tend to be mostly insoluble. Notice the change in the table. These are now mostly insoluble unless you mix it with the soluble cations. And you may ask, well, what are the soluble cations? Those are the cations listed here as always soluble on the solubility rules table. Okay, so ammonium, lithium, sodium, potassium, and rubidium and cesium will make hydroxide and sulfide soluble. In addition, if the cation is calcium, strontium, or barium, you have a substance that is soluble when combined with hydroxide or sulfide. Now, I'll be honest with you, we're being rather generous with our definition of solubility here, because barium hydroxide, barium sulfide, strontium sulfide compounds, they are sparingly soluble. They're not greatly soluble, but soluble enough that you could do some experiments at, high enough concentrations. Phosphate and carbonate, on the other hand, these particular anions are expected to be fully insoluble unless you mix them with the soluble cations NH4, lithium, sodium, potassium, rubidium, or cesium. Together, all of this forms the solubility rules. And what's enclosed here in the box is the parameter, or rather parameters, where you would expect to find solids in solution. Alright, so now, with solubility rules discussed, now we can actually look at the process of undergoing double displacement reactions and determining whether we're going to get a solid or not. Alright, so we're going to start with lithium sulfate and lead-2 nitrate. Lithium, in combination with anything else, has to have a +1 charge. Sulfate is SO4 with a 2- charge. Lead-2 is Pb with a 2+ charge, and nitrate is NO3 with a 1- charge. You use the charges to cross multiply and come up with the proportions. The 2 goes in front of the lithium, the 1 goes in front of the SO4, the 2 here goes in front of the NO3, the 1 goes in front of the lead. So you end up coming up with these proportions. Now notice that I have actually added the AQ symbols to PbNO3 because the presence of NO3 makes any ionic salt soluble. So you see nitrate, you see acetate, you see perchlorate or chlorate present, the substance is automatically soluble, or AQ. In the case of sulfate, the reason that's soluble is because it's mixed with one of the always soluble cations, specifically lithium, so this will be AQ as well. Alright, now, the two substances are ionic, and because they're being mixed with each other, we are going to undergo a double displacement reaction. We will exchange the partners, so keep lithium on the left side of the product side, and keep lead at the end of the product side. So now you're going to have lithium plus and lead-2 plus in that order, but the anionic partners are going to be swapped. Sulfate will no longer be with lithium, it now is with lead, and nitrate will no longer be with lead, it will now be with lithium. And it's once again important that you only bring the unit and its charge. The charge will remain the same in the double displacement reaction. So now you have lithium +1 and nitrate 1- mixing together. You have lead-2 plus and sulfate 2- mixing together. So you use the charges to come up with the proportions. 1 goes in front of lithium, 1 goes in front of nitrate. 2 goes in front of sulfate, 2 goes in front of lead. And since you want to go with the lowest ratio for the formula, the 2 in front of lead and the 2 in front of sulfate cancel each other out to give you the lower ratio of 1 lead and 1 sulfate. Another way to put it is that the charges are canceling out. You only need 1 lead and 1 sulfate to cancel out the charges. Alright, but now we have the lithium nitrate molecule and the lead-2 sulfate molecules on the product side. We need to determine the solubility of them. The first one, since it does contain nitrate and lithium, this is going to be soluble by default because it does contain the always soluble cations within it. On the other hand, lead sulfate contains lead, which is one of the cations, lead-2 plus to be most exact, which is one of the cations for which sulfate is completely insoluble. So this will now be a solid in terms of the physical state. And experimentally, what this means is that if you take a soluble solution of lithium sulfate and another soluble solution of lead nitrate and you literally mix them together, you expect to get solid lead sulfate crashing out from the solution. Okay, now in terms of balancing, we have 2 lithiums on the left side. We put a 2 in front of lithium nitrate to balance the lithiums. That gives us now 2 nitrates, and we also have 2 nitrates on the left side, so that's balanced. We have 1 lead on the product side, 1 lead on the left side, and we have 1 sulfate on the left side, 1 sulfate on the right side. The equation is now balanced. Altogether, this equation is known as the complete balanced equation, sometimes known as the complete molecular equation. Alright, now what we're going to do is we're going to take these 2 extra steps further. We're going to kind of deconvolute what's happening ultimately to each one of these ions. And what we first do is we take every substance that has an AQ symbol and we split it out into the corresponding ions. Okay? And this particular format of rewriting this equation is going to be known as the complete ionic equation. This can only be done though for substances that have the AQ symbol. So lithium sulfate you can rewrite as just lithium plus. You have 2 of them, so you still have to have 2 lithiums. Notice that the 2 is not written as a subscript, it's now written as a coefficient because the unit is not Li2 plus, it's Li plus. And you happen to have two of them, right? Sulfate, which is also SO4 2 minus, is written as its own, anion component. The two of them came from Li2SO4 AQ, so the two of them are AQ as well. PbNO3 2AQ splits up into Pb2 plus AQ and 2 nitrates AQ. Notice once again that the 2 has to come in front of nitrate because that is just a proportion. The unit is not NO3 2, the unit is just NO3 minus. So you have to bring that 2 in front as a coefficient. On the right side of the equation, we have 2 LiNO3s. So we have to write 2 Li plus AQ and 2 NO3s minus AQ. But the product that is a solid cannot be split up. It has to remain intact. In fact, let me put it to you this way. Any molecule that is not AQ, whether it's a solid, a liquid, or a gas, cannot be split up. So in these specific reactions, the precipitation reactions, we're going to be getting solids, which will be the one species that doesn't split up, but liquids and gases cannot be deconvoluted either. They have to be left as they are in terms of the molecular structure or the molecular formula that they are. Now, what you're going to notice right away when you split this complete balance equation into the complete ionic equation is that you have two lithium pluses AQ on both sides of the equation, and you also have two nitrate AQs on both sides of the equation. We refer to those species which are present on both sides of the equations without any change whatsoever to either the charge or the physical state as spectator ions. And the spectator ions, by definition, are not actually doing anything chemically speaking. So, what we end up doing is removing the spectator ions altogether from the equation, generating what we do call the net-ionic equation. So removing the lithium or cancelling out the lithiums and cancelling out the nitrates which are present on both sides of the equation exactly in the same format leaves us only with Pb2 plus AQ, SO4 2 minus AQ on the reactant side, and PbSO4 solid on the product side. Notice that these are the only things that have changed in some way or another. Specifically, they have changed in their physical state. This, from the point of view of chemistry, is the only thing that actually took place, chemically speaking, in your reaction. Everything else is still in the flask, still in the solution, it just hasn't changed whatsoever. So the net-ionic equation is the most direct, to the point means of expressing what has actually chemically happened.